Okay, we are now getting really close to actually being able to do our research with all the training. And so I'm actually going to give some things again so that hopefully it ties it all together. All right, this here is an inverting Schmitt trigger, right? Which is what we built in a programmable system on a chip, the PSOC device, with these resistor values, and we use the same. And it has a hysteresis where if the V in is between this range and V out is high, in order to go low, you got to go past this threshold. Then you're in a low state, and in order to go back high, the input has to go here. And it's referenced to ground. All right, and that's important. So what we have from prior work is here's the same inverting Schmitt trigger, maybe drawn slightly differently. This has a sine wave on it. And here's the hysteresis. And one thing we should point out is that it's not symmetric about zero, which we're able to fix this time around. Notice here, the way it's drawn, it's fixed around zero. Now, this project is different from the paper is that based on the values of the output voltage and max and min and these resistances, this width is calculated to be about 2.73 volts or 2.74. Ours, based on our V out, we've measured it to be about 0.46. All right. Also, this paper, the outputs were going between minus 15 and 15, and so it takes a lot longer to transition, where ours is only sweeping, changing between a change of 5 volts. All right, here we were going, well, we zoomed in here. V out is going from about 5 to minus 5, so it's about a 10 volt transition. But this op amp wasn't exactly rail to rail, which is causing this offset, which actually caused some troubles that I didn't realize the implications of that until we'd actually fixed it. So before this, or you say last year, we built it on a circuit board. That's an individual chip, right? And this year we switched to PSOC, which is an embedded system chip, right? Which has op amps and a microcontroller. Now the thing is that it doesn't have plus or minus power supply rails. This really only goes from about 0 to about 5 volts. And so we need to keep this hysteresis width, right, centered, right? Otherwise it wouldn't work. Now it's not really centered at 0. In retrospect, should have changed some things to make that happen. But this whole curve needs to be moved into the positive. It needs to be centered between 0 and 5. Ideally, we'd like it at 2.5, right? So what this is doing here is a current source, and the current is set so that when it passes through this resistance, right, it'll create something close to 2.5 volts. But if I connected this to here, these resistances would interact with each other and change the dynamics of the system. So we buffer it. And so this voltage is created with that current, right? V equals IR. And we put it in this op amp. And what it does is it translates this voltage here with a little error, right? But now I can hook it up to this resistance here and it won't affect the set point. All right. And these are called R2 and R3, even though in the paper it's R1 and R2. But notice the feedback here is coming in on the positive side. That's positive feedback. And that's why we get a Schmitt trigger. Now, something else so here, instead of being tied to ground or tying it to a voltage source externally here, right, what we did is we actually turned this not into just a DC offset, but also a sine wave, which is done right here. And this is the code, which I won't really go into. Right now, I'm testing it without the sine wave, so I've just multiplied the amplitude by 0. But and we've extracted the hysteresis width, and in my case, 0.46, and then I just divide the peak-to-peak input by 2. And what this does is the sine wave is kind of affecting the input here. We have to make sure the sine wave is smaller than the hysteresis width to make sure that it's um, stochastic resonance and you're not just driving it with a sine wave. All right. So what we're going to do is, where's that paper? Oh, here we go. So we've got that set up, right? And even though in our tutorial we did this part last, is we're going to input noise, right, with an RMS, and they call it theta, right? And they're calling it the noise variance. But really, variance and RMS are practically the same thing. So on this axis will be a frequency, right, which I'll show you in a second. And on this axis, it's the magnitude of this transform. And you're just finding the halfway point and then reading the frequency. And then this point here, right, which is about 1,000, and theta is 1. So this is inverse theta, by the way. So 0.97 is close to 1, and this point lines up to that 1,000. So this picture is this point right there. And then you just vary the noise along and measure the full width half maximum, and you plot it out. Now, yeah, this curve takes the transient, which they don't really show here, okay, which I'm showing. This is the time domain of it. And then you take a process which is similar to the fast Fourier transform, but it smooths it out, right? So you would just export these channels, export it into the full width half maximum file, and then rather than have a HP piece of equipment, we kind of programmed it here, which would be stochastic resonance scopy full width half max. Um, you have to change these to match yours, right? And we run it. Okay, and so there's the time domain, and we take the frequency spectrum, power spectrum, and turn it into this axis. Now in the poster, we probably want to make this square and get rid of this transient. Otherwise it won't look right. So we really want these plots, and notice how they're square and side by side, right? Even better would be to say this, some kind of arrow from here to that point, right? Would be even better way of showing that. So to create the plot, right, you set the V peak to peak noise and you extract the theta, right, and the full width half max, and you would enter it in just like you did for the signal to noise ratio. And then you've got the averages here, and you just go downward. All right. And just to point out is that from 0.7 to 2.1, the volts per division should be a half. So it zooms in and you're getting an accurate reading of the AC RMS, right? But when you go to 3, 5, and 7.5, you got to change this to 1. Otherwise, it clips. Um, and yes, the noise isn't visible because I've zoomed in on it and that DC offset has put it off the page. But there it is. All right. One could try using software AC coupling, but sometimes that causes some other issues. So it's just better that you know it's there because you can see you're reading it. And what measuring the AC RMS, it's there. You're kind of getting an idea. It's 67, 68, so that when you export it, save it, and run the Python file, that yeah, it's about 0.0679, and there's the full width half maximum. Now the lower frequencies can be a little bit tricky to measure. And the thing is sometimes I'll read for the same input of 700 millivolts, right? I'll read 74 or even sometimes 78 millivolts here. And I try to calibrate it a lot, but sometimes it's just kind of small and tricky to measure. Okay. Some things to point out is make sure that you're using your DC offset, right? Now your 700 might not work, and I'll show you what that looks like. So let's try 500. Now I'm getting an ACRMS of 48, but notice I'm not getting any transition. So if you're not getting a transition, like for instance, if I said, oh, start at 650, right? No transition, right? Don't write down 650, right? Now, some of you have larger hysteresis widths, like at 0.5, and so maybe you're not going to get any transition at 7. So you can try 700, you can try 750, or skip right to 800 millivolts, right? But just as a quick reminder, right, the peak to peak is like this kind of max scale on that noise source, and RMS is how we're characterizing it. The bigger the RMS, the more energy, and the wider that'll be. I'll just show you, like, yeah, I'm going to go to 5, and now notice it's saying AC RMS 494. So it might just be not quite scaled right. So see, I bring it up to 1. And then if I bring it up more, it stays at 502. It might not seem like a big deal, but that's, um, but accurately measuring that theta, the RMS of the noise, is super critical. And I'll kind of jump into that in a little bit. But anyway, for the full width half maximum, with the sine wave turned off, you just use the SR Scopy full width half maximum file, fill all this out, and you copy and paste it and save it to another file. All right. Which I have to double check. I called mine medium power, medium compensation, full with half maximum underscore parent. You use your name. Make sure that that's correct. And when you save all the data you've collected, all right, it's going to plot the average theta and the average full with half maximum, and it's going to use the standard deviations as um, error bars. Oh, something happened. Oh, I clicked something I shouldn't have. Well, that's not good. Um, I was working a second ago. That phrase is like the bane. Okay. So what this did was plot 1 over theta on the x-axis and the full width half maximum. And this is on a logarithmic scale because this relationship is supposed to be exponential. All right. There's something called the Cramer's rate, which is kind of the rate of change with the noise. That's 1 over the frequency. And the frequency will be some scale factor times e raised to a slope divided by theta, or in this case, it's delta u, which is actually the height of the barrier, right? So this is kind of this generic relationship. So what we do in the Python code is actually take the natural log of it, so it's a linear relationship, and just do a linear regression, and out comes the slope and the intercept here. And so that slope minus 0.47, right, would mean that the barrier height or the change in barrier height is 0.47, which is suspiciously close to the hysteresis width I measured. So that's very interesting. Are they related? Is it the same? Okay, but um, now I've done a linear regression here, but the thing is these last 3 points, it's kind of rolling off, right? These you can see are kind of bouncing around a straight line, but these are rolling off, and that's the op amp can't keep up. So in fact, the linear regression only does from these points on, and that line would be the plot of this. All right. So that's for medium power meteor compensation. But then this is the noise peak to peak from Scopy, the input, and here's the measured RMS, and you can see that it's relatively straight. Ideally, it'd be a perfectly straight line. But down here where it's small, it can be a bit tough to measure. And we can see up here where that can cause some trouble is that I did this a couple of days ago and it was really bouncing around because I wasn't calibrating as much. And you can see that it kind of caused some issues with this data, which is the signal to noise ratio thing. So, right, we have a plot here that shows, the peak in frequency, and then you extract the signal to noise ratio. Well, that's this plot right here. All right. So, and then something maybe dealing with Google Docs, I'm not quite sure if you know, as a, something is that if I want to insert a figure and you don't, the let me back up. The Python is saving that figure. So you don't have to cut and paste it or snip it, but you can just do insert image and it's already pointed to that project directory and I would just click the file I wanted and upload it. All right. But the fact that we can extract the curve and and it's The R squared is about 0.97, which is pretty accurate, right? Oh, for the poster, we'll get rid of this. This was me checking, it was like checking my work, if you will. Really means that there's stochastic resonance going on. Then what we do is we picked a sine wave at 1,000 hertz, right? Which means that 1 over theta would be, around 9, which if we go back here, that's 1,000 hertz. So we would think that the V peak to peak of 1 was giving us a full width half maximum of about 1,000. So that should be a good point to detect a 1,000 hertz sine wave. When we look at the signal to noise ratio versus theta, let me double check. One relates to 0.1, excuse me. So right around here, it's starting to pick up the signal to noise ratio. But you can see that between here and here, the signal to noise ratio it's above 8. So it if you read the paper, the full width half maximum needs to be near the detection frequency, but it's not exactly there. But that 0.1 is where it starts to really increase, and it doesn't really fall off to here. So the good news is that if you're in this range, you'll be detecting 1,000 hertz pretty easily. And even if it's bouncing around, that's pretty good. Although maybe the ones with smaller error bars are better, but that's a whole. We'll start to get into other research questions. So really, finish all that, and now the project is repeat the signal to noise ratio and full width half maximum work, except Ricardo, set your op amps high power low. That should make a fast Schmitt trigger. Eric, you set them low power high. That should make a slow Schmitt trigger. And then we can compare, right? Maybe the slow one stops working here and the fast one continues along this line more easily. Maybe, the fast one has a better signal to noise ratio. All right. But that's kind of a longer video than I like.